Hi, this is Mr. Ferris, and I will lead you through Lesson 8.2, where we will build confidence intervals for sample proportions. So here's a fairly simplistic example where there was a Gallup poll taken, and you can read there how many were in the sample size and how many said they either strongly supported or somewhat supported banning of animal racing. And we are supposed to create and interpret a 95% confidence interval for the proportion of people that fit that description. So one of the first things that we always want to do, and I think it's sometimes easy to forget, but thankfully they actually gave us a little reminder here. You are supposed to check conditions. So there are 3 conditions that we should already know how to check from Chapter 7. The conditions from Chapter 7 were 3 things. Because this is a sample proportion problem, we're going to build a confidence interval for the proportion. So this is a proportion scenario where we kind of imagine using a sampling distribution of a bunch of p-hats piling up. And the one p-hat that we have, we only get one, is 387 out of 1,017. So that one p-hat is one of many potential, kind of imagining in your mind the kind of imaginary sampling distribution. And those sampling distributions will be great to work with if they meet certain conditions. So first of all, we want to make sure that it's a simple random sample. Well, it doesn't really say simple random sample, but it does say random, so we will just say this sample is random. Ideally, it's a simple random sample, but probably in real life, they might not have done exactly that. It's a little more complicated in real life to get a good sample. Second condition is we want to make sure that n times p is greater than 10, and n times 1 minus p is greater than 10. That is going to guarantee that we can use a normal distribution for our model. But there's one great big problem with that. We know what n is. N is 1,017. But P, remember, is supposed to be the true proportion of people that support or somewhat support banning animal racing. Problem is, we don't know what true P is. And now we're presented with real life. A real life surveyor does not know before they start what the true proportion is. That's the whole point. That's what they're trying to estimate. So they're not going to know what P is before they take a sample to try to figure out what P is. So what do? Give up and go home? No. What you do is you use the next best thing that you have. We have p hat. We don't have p, but we do have p hat. P hat is our sample proportion. That's 387 out of the 1,017, which is approximately 0.381. So we do have that. So we can plug in 1,017 times 0.381 and check to see if that's greater than 10. Well, if you would just stop doing the things that you know you're supposed to do and just think a little bit. If you take 1,017 times the proportion of people that say they strongly, you are going to get 387, which should sound familiar. 387 is just the whole number of people that said they would strongly support or somewhat support. So it turns out these conditions now take on a different meaning. N times p hat is going to be the number of people that said yes to whatever the survey was. So clearly 387 is greater than 10, and then this calculation is going to turn out to be the number of people that said no. So if you take 387 from 1,017, you're going to get 630. So this condition takes on a little different flavor now. Instead of actually doing a multiplication, you can kind of forget about this multiplication stuff. Just count how many successes and how many failures, and if they're both greater than 10, you're good. So it's going to be a little bit easier to check this condition now that we are in confidence interval calculation mode. And then we just say something like, surely 387, oh, I'm sorry, not that one, 1017 is less than 10% of the population. Well, in this case, it would be less than 10% of all national adults. They're talking about national adults. (18 or over). So the sample's random. We checked our sample sizes. They're good. And the sample's not too big. So think about these three conditions. You're basically guaranteeing that the sample is random or representative. It's big enough, 387 and 630, but it's not too big because it's less than 10% of the population. Those are the three conditions that we check, and that guarantees that we can do what we're going to do, and that is we're going to proceed with a 1 proportion Z interval. It's 1 proportion because we just have one sample proportion that we're doing with. We are going to build an interval, and it's a Z interval because it's going to be based on a normal model since we know our sample sizes are big enough. That's what we're going to build. So if you remember, to build this thing, we have to have something plus or minus something times something. All confidence intervals look like that. The first thing is our statistic. Our statistic is the sample proportion. We already calculated that. It's 0.381. Plus or minus the critical value. The critical value is the number of standard deviations that we want to go out. How far out do we want to go? Well, it said a 95% confidence interval. And we know that means, 95%, that's 2 standard deviations. Well, but we were just going by that rule of thumb, that 95% of normal data is within 2 standard deviations. But that's a rule of thumb. That may or may not be exactly the right answer. So if you would go to your graphing calculator, and if you would do an inverse norm calculation, and if you do it correctly, some of you have the fancy calculator that does the center thing, and some of you have a calculator like mine that just you have to go left. So if you either do the 95% in the center or you do the 97.5% to the left, you find out that your critical value up there is not really 2. We said 2 was a rule of thumb, but it's really 1.96. Therefore, to be accurate, we are now, from this day forward, going to use 1.96. So the critical value, which is kind of like how many standard deviations we're going to go out from now on these confidence intervals, is 1.96. We're going to make that just a tad bit more accurate. And then we've got the great big square root formula for sample proportions. And again, remember that used to be p times 1 minus p, and we don't have p anymore. What we do have is p hat. So we will use p hat times 1 minus p hat. I always try to do that in my head so I don't have to write so much. So there's p hat times 1 minus p hat all over n, which is 1,017. That is the work for finding the interval. And then what we could do, if we just wanted to have an intermediate step, we could do all of that calculation here. And the reason that might be important is because all of this is something else that you should know. That's called the margin of error. And the margin of error might be something you want to report later anyway. So that would be an intermediate step that would be maybe nice. And then when you do the subtraction and the addition, you get the interval of 35.1% up to 41%. There is a 1 proportion Z interval. All nice and done. With one more thing to do. It did say not only create it up here, but it did say to interpret it. So we don't want to forget that. And my pen is not the greatest here. I'll try to write it out. This is the one where you say, I am 95% confident that the interval .351 to .410 contains the true, and here's where it gets a little long, the true percent of adults 18 and over who support or strongly support banning animal racing. Can't believe how messy my writing is, but this tool I have is not the greatest. So there we go. That's a complete problem. We've got conditions checked, which many people forget to do. Conditions are needed to be checked on all confidence intervals that you build. And you really should start there, because if they don't get met, then you really can't build one. And then you have the mechanics. We always want to show work for some sort of computation. And so the work would be this kind of 3 blank phrase there. And then we have our final answer, and then we have a interpretation in words, hopefully with better writing than I had. So there you go. Now, just for good measure, the question has been asked. Explain what 95% confidence means in context of this survey. And remember, confidence comes from that red and green bar diagram that I had you take a picture of the other day. What we know is if we could make lots and lots of these things in exactly the same way, then about 95% of them would capture the true percent of people who support banning animal racing. So I think I would start something like that. If we created many, if you want to, you can just say 100, but if we created many of these same intervals, or I should say many of these intervals in the same way, I think I should say it that way, many of these intervals in the same manner, then approximately 95% of them will capture the true percent of adults that favor banning animal racing. This is a confidence interpretation versus what we did earlier, which is a confidence interval interpretation. A little different wording and a little different meaning. So there you have it. There's a nice example of a specific confidence interval being created from a sample proportion. One interesting thing to note, the date of this survey is important to know. I don't know if anybody knows anything about animal racing, particularly horse racing, particularly a horse race that happens the first Saturday in May every year. This survey was conducted the week after the Kentucky Derby. And in that year, 2008, there was a tragic accident where a horse broke, I believe, 2 legs right at the end of the race. It collapsed on the track, and they brought out curtains and put it around the horse so the crowd couldn't see, and they euthanized the horse right on the track. So, do you suppose there is some, what would you call this, time bias or something? Just the proximity of this survey to a tragic accident might make people more likely to support banning animal racing. So my guess is these numbers are a little higher than they would have been on any other given year. Always got to be a little skeptical of any sort of statistical claim. All right, last thing we're going to do, the last little piece of the lesson, is to figure out how large a sample you need for something. This is a very common thing that's done. Before you go out and take a sample, you kind of want to know, well, how much do I need to have a certain confidence level and a certain margin of error that perhaps might be required, which is kind of like the margin of accuracy, or how precise you want the confidence interval to be. Therefore, we're going to do a little algebra. I hope you're ready for that. Haven't done that much this year. But just as a reminder, our confidence interval is always going to be the p hat plus or minus the critical value. We've been using 1.96 now for 95%, times the standard deviation of p hat. And don't forget, this little part here on the end, this is the margin of error. So if you read the problem, they give us that they want to be within 3%. That's the margin of error. And they want to have 95% confidence. And we're trying to figure out how large a sample. Well, how large a sample? That's n. We want to find n. So where does n come up in this formula? Well, if you think about what we're going to be using, it's going to be p hat plus or minus 1.96 because we're doing 95% confidence times the standard deviation formula, which is going to be p hat times 1 minus p hat all over n. So how are we going to write a formula somehow algebraically so we can solve for n and figure that out? Well, the other thing they gave us, remember, was the margin of error. The margin of error is this piece right here. This piece right here is 0.03. So that means we can just set that little suffix equal to 0.03, and we've got ourselves an algebraic equation that we can solve for n. So 1.96 times the square root of, actually we can, I guess we'll type it in, p hat times 1 minus p hat all over n. We want that to be within means less than or equal to 3%. We want that to be within 3%. That is our, actually it's an inequality that we're going to solve for n. With one problem, of course, we don't have p hat. Great. Nothing in the problem told us what the sample proportion was. So now we got a little problem. We don't have all the givens that we need to solve for n. So we have to do a little thinking here. And now, again, you got to put your algebra hats on. We want this to be less than or equal to 3%. So we would, if we don't know what p hat is before we sample, that's again one of these dilemmas. We don't know what p hat's going to be until we sample p hat. And we don't know how big a sample size that we need, so we can't sample before we get the sample size. So it seems like we're in this infinite circle. Well, if we want to have the most conservative answer, then we could just make up a p hat that might be, say, the worst case scenario. What would be the worst case scenario that would drive this numerator to the largest possible? We would want to pick that number so that the n would work out to be even good enough if this was the worst case scenario. So what would give us a numerator that is the largest, would have the biggest margin of error? Well, just go through some of the possibilities. If p hat is 0.1, then 1 minus p hat is 0.9. The product is 0.09. If p hat is 0.2, 1 minus p hat will be 0.8. Product is 0.16. That's bigger. So if you keep going up the ladder, all the way up to 0.4 times 0.6, that would be 0.24. You get to the middle one, which is 0.5 times 1 minus 0.5. There's your magic number, because 0.5 times 0.5 will be 0.25. That's the largest possible numerator you could get. So we are going to assume that p hat is the worst case scenario. That way, when we calculate n, we will be guaranteed to have a large enough n to keep our margin of error at or below 3%. So we have to do a little thinking and a little common sense to substitute 0.5 when you're not given something. Now, sometimes the problem might say, well, last year, it was 46%. Well, if that's the case, you can use 46% for p hat. But if they don't tell you anything, you want to use the conservative 0.5 and 0.5. Now we just solve for n using algebra, and I'll just show you a little shortcut here that should be helpful for doing these in the future. If you do a little algebra, you know that you can divide the radical up into numerator and denominator. And then if you can imagine multiplying both sides by the denominator of radical n and at the same time dividing both sides by 0.03, hope you've had enough algebra to be able to think what that's going to be like in your head. If we do both of those steps simultaneously, this is what we're going to get. Now what it looks like, of course, it looks like I just swapped these two things with each other. But really, I did two algebraic steps. I multiplied both sides by the square root of n, and at the same time divided both sides by 0.03. So it's kind of what I would call the switcheroo shortcut. And it makes it really nice because if you're solving for n, all you have to do now is compute this stuff on the other side. And that stuff on the other side, actually, did I write that down? I'm not sure I wrote that down. But the bottom line is, if you, what you're going to have to remember, though, of course, is whatever you get here, which I don't have written down, that's going to be less than or equal to the square root of n, so you have to square both sides to get that n is greater than or equal to 1067.1. So we just solved for n, and we know now that n has to be larger or equal to 1067.1. Now again, we got to think, what is n? N is a sample size. N must be an integer. N must be an integer. Therefore, if we have to have an integer that's greater than or equal to 1067.1, then we want to use 1068. So here's one of those weird times where we might have to break the rule of rounding. Normally you would round down, but we want n to be greater than this number, and it has to be an integer. So the next integer that's meets those two criteria, that it's an integer and it's greater than 1067.1, would be 1068. Therefore, you must always round up. You always round up to the nearest whole number when you're solving for sample sizes. That's kind of a rule of rounding that is kind of different for this scenario. So anytime you're solving for n, and you'll be doing that frequently, you'll want to round up. So there you go. There's a complete problem of confidence intervals, and then a complete problem in solving for sample size. So hopefully that will give you a good example that you can use, and if you need to, you can even go back and watch some of these steps again. So I will see you in class.